Morning, or well, whenever you might be watching this. This video, we're going to run through day one of section 7.5. So we're going to talk about how to solve equations that contain exponential expressions in them. So, as a quick little EQ is how can I solve equations that contain exponential expressions? So our warm-up is a city with a population of 250,000 is growing by 0.8% each year. What will the population be in 15 years? So we have an initial value or a start value of 250,000. We aren't given the year, but that's okay. We can assume it's just present day. Is growing, so we're going to have exponential growth by 0.8%. Now remember, when we have a percentage, we need to divide that by 100 or move the decimal point to the to the left. And that will give me the percentage expressed as a decimal. Now, okay, the calculator wants to tell me scientific notation, which doesn't help me. So I'm just going to manually move or insert two zeros there. So 0.8% would be 0.008. And then the question is, what would the population be in 15 years? So if we recall, for these exponential growth and decay problems, we had an equation that looked like this. Okay. A equals A being the future value, P is the present value, 1 plus R, which is the percentage rate change, to the power of T. So we have A equals 250,000. Times 1 plus 0.008. And T, in this case, we want the population in 15 years, so we're going to go to the 15th power. Now, what we're going to do with that is I can go to my calculator and just type in 250,000 times 1 plus 0.008, or you could just type 1.008 to the 15th power. And that will give me, since we're talking humans, in population, we're going to round that to 281,740 will be the population in 15 years. So that's solving an expression with exponential, or solving an exponential expression, just plugging a number in for the exponent. What we're going to look at today is a question like this. So we're not going to answer this question right now. We're going to wait till the end. But if that same city was growing by 0.8% per year, how long will it take to reach 500,000 citizens? How many years will it take to get to 500,000? And we're going to learn how to solve things like that today. So to start with, we're gonna start a little bit simpler. Okay, so let's just look at an example exponential equation like 5 to the x equals 20. So 5 raised to what power equals 20? Well, I know 5 to the first power is 5, and 5 to the second power is 25. So the answer's got to be somewhere between 1 and 2. And you could get there by guessing and checking. It's going to take you a while to, especially because with these answers, we want around usually 3 decimal points. So it's going to take a while for you to, really nail the answer down to the thousandth place if you have to just guess and check. But what we're going to do here instead is we're going to actually use what we know about logarithms to rewrite this equation. We'll see that we can actually solve it very simply. So if we remember, this is called the base. This is the exponent. And the other portion of a logarithm is called the argument. So to rewrite this as a log, I would have log base 5 of 20 equals x. So I haven't solved this. All I've done is rewritten it. So instead of an exponential equation, it's logarithmic. But what I can do now is I can actually type log base 5 of 20 in my calculator. And remember, there's no log base 5 button on a calculator. But what we saw is the change of base formula allows us to do this by typing log of 20 divided by log 5. Okay, so if I type log 20, close the parentheses, divided by log 5, I get 1.861. That is the power. So that means we have to do 5 to the 1.861 power to get very close to 20. Okay. And again, we're rounding. So you could say this is approximately equal to x, but for our conversation, we're good there. Okay. And just so I could check my work, 5 to the power of 1.861 is 19.98. And that's why it's important to have at least 3 decimal points, because even with 3 decimal points, I'm not really even that close to 20. So we could go further, but we'll stick with 3 for now. So exponential equation, if you see x in the exponent and you need to solve for x, we're going to use logarithms to solve. Okay, so this problem is a little bit more difficult. Oh my goodness, this problem's a little more difficult because there's more steps involved, but the concept is still the same. I see my variable in the exponent. Now, I didn't put parentheses when I made this problem, but the exponent isn't just x, it's negative x plus 5. That whole thing is the exponent. So I'm going to go ahead and rewrite this as a logarithm. Log, I'm going to use the base, that base number of 4, and then the argument is 137, and that's going to equal negative x plus 5. So now my next step is to type log base 4 of 137, which again is log 137 divided by log 4. And that's going to give me 3.549. So just so we have for the completed notes, 137 over log 4. Whoops. Log 4 equals negative x plus 5. So 3.549. And now it's just our regular algebra. There's no longer logs or exponents. Now it's just how do you get x by itself? Well, I want to subtract 5 to both sides. And so that's going to give me 3.549 minus 5 is negative 1.451. This is negative 1x, so I'm going to divide by negative 1 on both sides. Dividing by negative 1, of course, just changes a negative number to a positive, so we get positive 1.451. Okay, which means if you were to take this number, 1.451, and replace x with it, we would get a value that's very close to 137. So that's the idea, that's the concept behind what we're doing here. So yeah, exponential equation, x in the power, you're going to use logarithms. Go ahead, pause the video here, try these 2 quick, and then we'll look at one previous example and get back to our warm-up. All right, so if I rewrite this as a log of base 3 of 14 equals 2x plus 1. Log, I'm not going to write this one out, log of 14 over log of 3, 2.402 equals 2x plus 1. Now we just let regular algebra take over. Take away 1 from both sides. I got 1.402. Probably could have done that without a calculator. And then we're going to divide by 2 on both sides. 0.701 is my missing value. Okay. Yeah, so there's that first one. And then here we're going log base 10 of 250 equals 5x minus 7. Now log base 10 is just the log button, so I can actually get away with just typing log 250. Just to prove that point again, if I were to do this divided by log of 10, I'm going to get the exact same number. So this is 2.398 if I round to the thousands place. Because that 9 would round the 7 up. And from here, we're going to add 7 to both sides. So that's 9.398. And then divide by 5. And we're done. So while it does look, these problems do look a little bit trickier, you're still dealing with Just one more new algebra step that's introduced. So 1.880 is how that would round. So, yep. Rewrite as a logarithm, and then we move on. The only thing that can get in your way is if you have something that looks like this. So negative 87 equals negative 3 times 2.5 to the x. Right here is my base number and my exponent, right? That power of x is only applying to the 2.5. So before I can rewrite this as a logarithm, I have to get rid of that negative 3. And I'm going to do that just using basic division that we would do if it was negative 3 in front of x. So I'm going to divide negative 87 by negative 3, and then I'm going to go ahead and rewrite this as a as a logarithm. So 2.5 to the power of x. Now again, this is backwards, or it's written opposite of all the other ones. This is my base number, not 29. Okay, the base number has to have x as its power. So I'm going to go log base 2.5, which again, logs can have decimal bases, they just can't have negative bases, equals x here. So I got log of 29 divided by log of 2.5. Whoops. 2.5. So it's 3.675. And there's nothing else with x, so we're done. So this one, we just had to have one step before we rewrote it as a log, and that was to get rid of that front negative 3 number. So just be careful of that. If it would have been like a -7 at the back of this problem, then we would have had to add 7 to both sides. But yeah, I mean, again, it's the algebra that you've known and done for years. We're just adding one more new step to it. All right, so let's revisit that problem from earlier. How long will it take this city to reach 500,000 citizens? Okay, so here's what the equation would look like. Here's our starting value of 250,000, and here's our future value, which we know is 500,000. What we don't know is how much time is it going to take. So my exponential portion of this is the 1.008 to the x power. So just like in the previous problem, I need to get rid of the 250,000. So I'm going to divide both sides by 250,000. Okay, there that cancels. 500,000 divided by 250,000 is just going to give me 2. If I were to type that into a calculator, 1.008 to the x. So now here again, I'm going to write this as a logarithm. So log, the base is 1.008. The argument is 2, and that's going to equal the number of years that I need to reach 500,000. So we're going to go log 2 divided by log of 1.008. And that's pretty close to 87 years. So it's going to take about 87 years for that city to double in population up to 500,000. So using what we learned in this video, we can now solve exponential equations when you have a present value and you want to know how much time will it take to get to a future value. This is used a lot in chemistry and sciences when you want to know how long will it take, what's the half-life of something, or how long will it take for there to be a certain amount of a substance remaining. So to summarize, how can I solve equations containing exponential expressions? If I see this, 3 to the x equals 10, I do this, log base 3 of 10 equals x, and then we type this in the calculator. That'll do it. One more video.